So in this lecture, I will speak about the Fredholm alternative. So here is the setup. X is a separable Hilbert space. And we have on X an operator A from X to X, which is symmetric and compact. Symmetric and compact means, remember, that the operator is linear, that the scalar product of AX with Y is equal to the scalar product of X with AY for all X, Y in X. And finally, compacity here means that if you have a sequence xn in X, which is bounded, so for which there exists C0 finite, such that xn is bounded by C0, then the sequence AXN is relatively compact. So this is the setup of this lecture. And I want to discuss the solutions of two equations. Consider existence and uniqueness of solutions of the following equation. So the first one, I will fix a z in X, and I want consider lambda a scalar lambda, and consider the equation lambda x minus ax equal to z. I want to check whether for a fixed z I can find x which solves this equation. So this is one equation, and the second equation, it's what I will call the homogeneous equation, is the equation lambda x minus ax equal to 0. So I want also to see whether, of course there exists always a solution to this equation, because I can take x to be 0, and this is a solution, but there might be more than one solution. So let me represent by n of lambda the set of solutions. So all points x in X, such that lambda x minus ax is equal to 0. And what I want to observe is that, well, I have here an operator, lambda minus a, from X to X. And actually, this set is the null set of this operator. So this operator sends X to lambda x minus ax. This is clearly a bounded linear operator. So if I consider the null space, so the set of X such that lambda x minus ax is equal to 0, this is exactly this set. So n lambda is actually the null space of the operator lambda minus a. And as a null space, we know that this, and you can check, that this is a closed linear subspace of X. So I want to investigate existence and uniqueness of this solution, and I will use informations on uniqueness of that solutions in order to guarantee existence of these solutions. So my next step will be to state the main theorem of this lecture and to prove it. So I just recalled here that I'm interested in this equation. This is the homogeneous equation, and I introduced that space, which is a closed linear subspace of X, which corresponds to the null space of the operator lambda minus a. And the theorem, which I want to prove in this lecture, is the following. So I'm fixing lambda different from 0 and z in X. And I'm considering this equation, so maybe let's call it EQZ. And the theorem states that E QZ has a solution if and only if Z belongs to the orthogonal space of n lambda. So n lambda perp. So remember, X is a Hilbert space, so X can be represented as this space plus its orthogonal, because n lambda, as we have seen, is a closed linear subspace of X. And so what this theorem is telling you is that if lambda is different from 0, then this equation for a fixed Z has a solution if and only if Z belongs to the orthogonal space of n lambda. And you see here that this means Z belongs to the orthogonal space of n lambda. It's the same thing as requiring that Z y is equal to 0 for all y in n lambda, which means for all y which solves the homogeneous equation. So saying that Z belongs to the orthogonal of n lambda is the same as requiring that Z is orthogonal to y for all y in n lambda. So this is the theorem which I want to prove. And the proof is based on the theorem I proved in the previous lecture. And remember its statement. Its statement was saying that since A is a symmetric compact operator, we can find a basis of X made of eigenfunctions of A. So the theorem was telling us in particular that if X belongs to X, we can write X as a sum of xj plus a sum xwk, where xj are eigenfunctions, and let me represent of the operator A. The eigenvalue of xj, I will represent it by lambda j. So this is the eigenvalue associated to xj. xj is an eigenfunction which has norm equal to 1. So we know that they are orthogonal and among themselves. And what are the wk's? Well, the wk's, on the other hand, are such that A of wk is equal to 0. So they are in the null space of A. They are also, they have norm equal to 1. And they are orthogonal among themselves. So wk, wj, it's equal to 0 if k is different from j. And also the x and the w are orthogonal, which means that the xj and the wk form an orthonormal basis of x. Let me just point out that maybe these sums are, there are no terms in these sums. So maybe the orthonormal basis is made only of wk's, or maybe only of xj's, or they can have both. These sums can be finite or can be infinite. And well, of course, since I'm assuming always that the Hilbert space X it's different from a point 0, one of these sums it's non-zero. So there is at least one element, one x1 or one wk. So the proof of this theorem will be based on this fact, which we proved in the previous lecture. So let me repeat. We have an orthonormal basis made of xj's and wk's. Here are the properties of the wk's. Here are the properties of the x. And just to mention that I'm writing these sums as infinite sums, but they might be finite or they might be empty. So maybe this sum is empty and we have only wk's on our basis, or this sum is empty and we only have xj's on our basis. We can have both. At least one of them is present, and each sum might be countably infinite or finite. So I just recall that lambda is different from 0 and z belongs to x. So I want to consider two cases. Case 1 is that lambda is different from lambda j for all j. So remember, the lambda j's are the eigenvalues of the operator A. And I'm assuming that lambda is different from all of them. So let me recall that I can write x as the sum of x, xj, xj, plus the sum of x, wk, wk. And as I mentioned, these sums might be empty, might be finite, or countably infinite. Since x is given by this expression, what is lambda minus ax? So I'm taking any point x in x. I know that it can be written in this way. And now I'm computing lambda minus a of x by writing x on the autonomal basis xj wk. And I want to consider that lambda x minus ax is equal to z. So z is fixed. And by writing what is lambda minus a, I have to just look at first what is lambda x. So lambda x is just multiplying these sums by lambda. So I get a lambda here inside. And now if I apply a to x by linearity, what I'm doing is applying a to this term. But by linearity, this is applying a to xj. And xj, it's an eigenfunction associated to the eigenvalue lambda j. So axj will be lambda jxj. And here, if I apply a, I'm applying a to wk. But a wk is 0, so this piece will disappear. So lambda, by this consideration, what I get is that lambda minus ax, it's equal to the sum of lambda minus lambda j x xj xj plus k larger than 1 lambda x wk wk. Here, because a of wk is 0. So this is what I get for lambda minus ax. And now I want this to be equal to z. So I can also write z on the basis xj wk. And by doing that, what I get is that this is equal to the sum over j of z xj xj plus sum over k z wk wk. Now, if I want these two expressions to be equal, this means that for all j's, this factor, this scalar, has to be equal to this one, and this one has to be equal to this one for all k. So from this identity, that lambda x minus ax equal to z, what I get is that for all j, this expression has to be equal to that one, and this one to that one. So let me write this. I need that lambda minus lambda j x xj is equal to z xj. And I also need lambda x wk to be equal to z wk. Now, since lambda minus lambda j, it's different from 0, I can divide this identity by lambda minus lambda j. And since lambda is different from 0, I can also divide this identity by lambda to get that xwk should be equal to zwk divided by lambda, and xj should be equal to z lambda minus lambda j. So I get from this identity the scalar product of x with wk for all k, and the scalar product of x with xj for all j. So remember that x is given by the sum, and I just computed that if I want this inequality to hold, then xxj should be given by this, and xwk should be given by that. So I have a candidate as a solution. If there is a solution, the solution has to be this one. So I will just replace xxj by its expression, which is zxj lambda minus lambda j xj, and I will replace xwk by its expression, which is this one. So now so this is my candidate. So if there is a solution, it has to be given by this expression. Well, now does it make sense? So is this an element of X? So what I need to guarantee for that to be an element of X is that zxj square, the absolute value square divided by lambda minus lambda j square plus that this is finite. If this is finite, then these sums define an element of X, and therefore there is a solution for the equation lambda x minus ax equal to z. So I have just to check that this is true. But this is clearly true because, well, on the one hand, you see that the first sum, it's finite because I'm assuming that lambda is different from 0. So this is equal, so the second sum, it's equal to 1 over lambda square zwk. And this is always finite because this sum here, it's bounded by the Bessel inequality to the square of the norm of z. So this sum, it's finite, and lambda is different from 0. So the second sum, it's clearly finite. And now, for the first sum, I will just bound it by the supremum in J of 1 over lambda minus lambda j square times the sum of z xj square. So again, this sum, it's bounded by the square of the norm of z, because these xj have all norm equal to 1 and they are orthogonal. So this is by Bessel inequality again. So what remains to be shown is that this supremum, it's finite, but this supremum is finite because we know that the lambda j's converge to 0. So since lambda is different from 0, let's say that lambda it's a real number. So here is, let's say, lambda. we know that for j, all the lambda j's are real numbers, and their limit is equal to 0. So if I fix an epsilon and I take lambda minus epsilon, I know that starting from some j0, they are all less in absolute value than lambda minus epsilon. On the other hand, there are only a finite number of them which are larger than lambda minus epsilon. And since they are all different from lambda, there is a distance. So this infimum, if I take the infimum over j of this expression, this is strictly positive, and therefore the supreme of the inverse, it's bounded by some finite constant C1. So from the fact that the lambda j's are converging to 0, we can guarantee that lambda minus lambda j is larger than some epsilon, which is strictly positive. So that there exists an epsilon positive such that the absolute value of lambda minus lambda j is strictly positive, which means that the supreme of the inverse is bounded by some constant C1. So this proves that indeed this x given by this sum solves the equation z, which proves that if lambda is different from all j's, this equation has a solution, which is given by this expression, and this is the unique solution, because we have shown at the beginning that if x is a solution, it has to be given by that. So we just proved that if lambda is different from lambda j for all j, then this equation has a unique solution, which is given by this expression. So we proved that in the case lambda different from lambda j for all j, this equation has a unique solution. So now let's consider the solution, the second equation, the homogeneous equation. Let's again write x in our orthonormal basis. And let's write that lambda minus ax, it's equal to 0. So what is lambda minus ax? So let's apply lambda minus ax to the sum. This is the sum. We already computed that. That's lambda minus lambda j x xj xj plus lambda x wk wk. So we computed that in the previous step. And we know that this is equal to 0, so this sum, it's equal to 0. Since all these vectors, xk and xj and yk and wk are orthogonal and have norm equal to 1, for this sum to be 0, every scalar has to be equal to 0. So from this identity, we deduce that lambda minus lambda j x xj it's equal to 0 for all j, and that lambda x wk it's equal to 0 for all k. So since lambda is different from 0, from this equation we deduce that x wk is equal to 0 for all k. And since lambda is different from lambda j for all j, from this equation we deduce that x xj it's equal to 0 for all j. So if we go back to this representation of x, we have that the scalar product of x with xj is equal to 0 for all j, and the one of x with wk is also equal to 0, and so this means that x is equal to 0. Which means that the homogeneous equation has only one solution, which is x equal to 0. So we just proved that in this case, so if lambda is different from all lambda j, and lambda is different from 0, we proved that there exists a unique solution so that for the equation lambda x minus ax equal to z, and also that there exists a unique solution for the equation lambda x minus ax equal to 0. This means, in particular, that the set n lambda, which is the null set of lambda, and this solution is x equal to 0, right? So this is telling us that the null set of the operator lambda minus a is the point 0, so that n lambda, the null space of the operator lambda minus a, is 0, and therefore that n lambda perpendicular is equal to x. And so the theorem was saying that, well, this equation has a unique solution if and only if z belongs to the orthogonal space of n lambda. Well, so this is true because under this assumption, the orthogonal space is the whole space, and this equation has always a unique solution. So the theorem holds when lambda is different from all lambda j's, right? Because on the one hand, this has always a solution, and on the other hand, the orthogonal space of n lambda is the entire space X. So what we really need to consider is the case 2, in which lambda is equal to one of the lambda j's. So I'm now assuming that lambda, case 2, lambda is equal to one lambda j, not j0, for some j0. So let's see first what is the space n lambda, which coincides with the space lambda j0, and this is the set of all x such that lambda j0 x it's equal to ax. So this corresponds exactly, so lambda j0 it's an eigenvalue. This identity means that x it's an eigenfunction, so this is the eigenspace associated to lambda j. And we proved in the previous lecture that lambda j has finite multiplicity, which means that this space it's a finite dimensional space. So it's a finite dimensional space, and in our basis, so we obtained a basis xj of j larger than 1. So this finite dimensional space is generated by a finite number of vectors xj. So let's say that this space is the closed linear space, or the linear space generated by, let's say that xk, or maybe xl, up, or p up to q. Right, so I'm taking in this countable family of eigenfunctions the ones which are associated to the eigenvalue lambda j0. So this is just a comment on n lambda. In our case, n lambda is just the eigenspace associated to the eigenvalue lambda j0. We proved that this space it's finite dimensional in the previous lecture. So let's say that this space is the space generated by the eigenfunctions going from p, xp to xq, where p is less than q. And suppose here that I change the order of this eigenfunction to have the ones which are associated to this eigenvalue to be the ones running from p to q. So now let me prove the theorem. So the theorem tells me that there exists a solution. So requires me to prove that there exists a solution of the equation lambda x minus ax equal to z if and only if z belongs to the orthogonal space of n lambda j0 orthogonal. Okay, so let's first assume that z belongs to the orthogonal space lambda j0. So this means that since z belongs to this orthogonal, this means that z is orthogonal to all these elements j from going from p to q. Well, so if this is true, I can introduce, so let me erase, I can write down a candidate for the solution of this equation. I want my candidate x will be the following one. It will be the sum j larger than 1 of, so remember before I had xj, lambda minus z xj, lambda minus lambda j xj plus sum over k 1 over lambda z wk wk. So this was my candidate. The problem now is that lambda is equal to lambda j0. So what I will do here is that I'll just sum for all j's which belongs to n minus the set going from p to q. Right? Because these are exactly the sets in which lambda it's equal to lambda j. Right? Lambda j running from p to q, it's lambda j0. So I'm removing from this sum all j's from p to q, which means that I'm removing all j's for which this difference is equal to 0. Since this difference is now not equal to 0, what I claim is that that this sum makes sense, so that this is indeed an element of x. So let me show that this sum defines an element of x. So again, to prove that this sum defines an element of x, I need to show two things. First, that the sum for k larger than 1 of 1 over lambda square zwk square, it's finite, but that we have seen that it's indeed true because lambda is different from 0, and this sum it's finite because z it's an element of x. So this one it's okay. And I have also to show that this sum it's finite, so the sum from j, which does not belong from p to q, it's finite. But again, I will estimate that sum as the supremum for g not in the set pq 1 over lambda minus lambda j square times the sum for all j now of z xj square. So this one is bounded by z square, the norm of z square, which is finite. And this one, so this is, we already shown that it's finite. So now we have to bother with this one. Well, but here what I'm doing is that I'm fixing an eigenvalue lambda j0. And so all the other lambda eigenvalues, so there is one whose absolute value is strictly larger, one which is strictly smaller than that. So this difference, since I'm removing from the sum all eigenvalues which are equal, I'm removing lambda j0, so I'm removing all eigenvalues which are equal to lambda j0 in this supremum, this distance, it's larger than the minimum between this distance and this distance. And therefore, this distance, it's always bounded below by a strictly positive constant, and therefore the inverse, it's bounded above by a finite constant C1. So let me repeat this argument. When I'm removing from this supremum all j's between p and q, I'm removing in this supremum all eigenvalues which are equal to lambda j0. And by removing them, so if I look at the absolute values, I have one which is strictly larger than lambda j0, one which is strictly smaller than lambda j0, and no one in between, because this sequence is converging to 0. So it cannot accumulate around lambda j0. So if it can't accumulate around lambda j0, this distance and this distance are strictly positive, and therefore this supremum is finite. And this proves, therefore, that this sum is finite, and therefore that indeed x given by this sum defines an element in xk. Now I claim that this element is a solution, and to prove that it is a solution, what I have to do is to compute lambda minus a x. And when I compute lambda minus ax, you see that here I will get lambda minus axj, so this will give me lambda minus lambda j, which will cancel with that. So this, it's equal to the sum for all j not in pq of z xj xj. And here, when I compute lambda minus a of wk, I get lambda wk. The lambda will cancel with this one, and this becomes a sum in k of z wk wk. And now I just recall that z xj it's equal to 0 for j between p and q. So I can add in this sum the j's between p and q, because this scalar it's equal to 0. So it doesn't matter if I include these terms in the sum or not. So actually I can perform a sum over all j's, and once I include these terms, what I get, that this is exactly the formula for z, and therefore indeed lambda minus ax it's equal to z. Therefore we proved that indeed if z belongs to the orthogonal of n lambda, so if z belongs to the orthogonal of n lambda, then there exists a solution of the equation lambda x minus ax equal to z, which is given by this expression. Now let's assume that there exists a solution to the equation lambda x minus ax equal to z. So suppose that there exists a solution to this equation. I want to prove that z belongs to the orthogonal of n lambda, which means that z xj it's equal to 0 for all, or 0 x or 0 y it's equal to 0 for all y in n lambda. So let's take y in n lambda. So this means that ay it's equal to lambda y. Y in n lambda means that y belongs to the null set of the operator lambda minus a, which means that ay is equal to lambda y. And let's show that z is indeed orthogonal to y. So in order to do that, we have to apply compute zy, the scalar product of z with y. But z is the solution of this equation, so z lambda x minus ax y. So I just replace the fact that z is the solution of this equation. So this gives me lambda xy minus axy, but a is symmetric, so this is equal to minus xay. But ay is lambda y. And since lambda is now equal to one of these lambda j's, I know that lambda is real, so that this is equal to lambda x y minus, I can take it out and use the fact that it's real to have here lambda, and you see that this is equal to 0. So we proved that indeed, if there exists a solution to this equation, z has to be in the orthogonal of n lambda, and this completes the proof of the theorem, since we have seen that, well, in this case, if I have a solution, then z belongs to the orthogonal of the null space, and if z belongs to the orthogonal of null space, I have a solution. On the other hand, if in the case 1, lambda is different from lambda j for all j, then if there is a solution, but this is always true, then z belongs to the orthogonal, but this is also always true. So this is always true because this space is equal to x, and this is always true because there is always a solution. So in case 1, the equivalence is trivial because both requirements always hold. So let me just make a remark on this proof. Let's assume that lambda is different from 0 and that lambda is different from lambda j for all j. And let me fix z in x. Let me consider the equation lambda x minus ax, it's equal to z. Then I proved that if lambda is different from lambda j for all j and different from 0, I proved that there exists a unique solution to this equation, and I obtained even its explicit formula, which is x, the sum j larger than 1 of z xj divided by lambda minus lambda j xj plus sum for k of 1 over lambda z wk wk. So we proved in the middle of the argument of case 1 that actually this equation has a solution. The solution is unique, and it's given by this formula. So now let's see. X square, I can compute x square by this formula. This is exactly by Parseval identity given by this sum. And I claimed that, that this expression, since lambda is different from lambda j and the lambda j's are converging to 0, that this 1 over this expression, it's bounded by a finite constant, and since lambda is different from 0, this is bounded also by finite constant. So by taking the maximum of this constant, I can bound this expression by C1 times And if you observe what I obtained, again by Parseval identity, this is equal to the square of the norm of z. So this is bounded by C1 z square. And this constant is independent of z. It depends only on lambda. So this constant C1, it's a constant which depends on lambda, but not on z. So we proved that you fix a lambda. Now you consider any z. You prove that there exists a solution, and the solution satisfies this inequality. So now what I want to consider is the following: the operator lambda minus a. The existence of a solution for all z's means that this operator is surjective, which means that it's onto. Right? It means that for all z, I can find x such that lambda x minus ax it's equal to z. So this operator, as an operator from x to x, it's surjective. Now I claim that it's also injective. Why is it injective? Well, to prove that it's injective, I have to show that if lambda x minus x ax is equal to 0, then x it's equal to 0. Well, but if lambda x minus ax is equal to 0, this means that x, and let's say I claim that x is equal to 0. If x is not, assume that x is not 0, let me get a contradiction. If x is not equal to 0, this means that lambda it's an eigenvalue of a. Well, and we have seen that if lambda it's an eigenvalue of a, then lambda it's either equal to some lambda j or lambda it's equal to 0. But I assume that lambda is different from 0 and lambda is different from all lambda j. So I get a contradiction. So this means that this operator lambda minus a, it's injective, because the unique solution of this equation is x equal to 0. So I just proved that if lambda is different from 0 and lambda is different from lambda j, this operator is a bijection from x to x. So I have an inverse, which is lambda minus 1, lambda minus a at minus 1, which goes from x to x. And so this is telling me, well, so lambda minus a minus 1, it's sending z to x. So the solution of this equation is x equal lambda minus a minus 1 z. So if lambda is different from 0 and for all lambda j's, lambda minus a it's a bijection, so I can define lambda minus a minus 1, the inverse. And what I get is that the inverse, this inverse operator, gives me exactly the solution of this equation. So if I want the solution of this equation, I just have to apply to z the operator lambda minus a minus 1. And what this inequality is telling me is that, well, x, it's lambda minus 1z. So let me write this as lambda minus a minus 1z squared. What the sequence of inequality is telling me is that, let me forget the square, that this is bounded by a constant which depends on lambda of the norm of z, which means that this operator, it's a bounded operator. So not only there exists an inverse, of course we know that since this operator is linear, the inverse it's linear, but the inverse it's also a bounded operator. So what we just proved is that if lambda is different from 0 and different from all lambda j's, then the operator lambda minus a minus 1, it's a bounded linear operator from x to x. So let me prove a corollary to the previous theorem. So I'm taking here a lambda different from 0 and a z in x. And let's suppose that lambda x minus ax equal to z has at most one solution. Can't have two or more. I'm not saying that it has, but what I'm saying is that if it has, it's unique. Then I claim that first there exists the operator lambda minus a minus 1, and that the solution x it's given by lambda minus a minus 1 z. So this result is telling me that uniqueness, so here I'm assuming uniqueness of this equation, implies existence. So what I'm saying is that uniqueness implies existence. Right? Here I'm assuming that I have uniqueness of this equation, and here I'm saying that, well, then this equation has a solution, and this solution is given by this element because there exists lambda minus a as a bounded operator. So this is a bounded operator. It exists and it's bounded, and the solution is given by that. So proof. Well, what I claim is that lambda has to be equal to lambda j for some j. So what I want to show to you is that if there is at most one solution, then lambda j, it's different from lambda j for all j. Right? What I'm saying is that if you have uniqueness, then lambda has to be different from lambda j for all j. And what I will do is I will proceed by contradiction. Suppose by contradiction that lambda it's equal to lambda j for some j. Well, then you take a solution. I will show that there exists more than one solution. Let x be a solution. I claim that x plus alpha xj is a solution. And why is that so? Because, well, if you apply lambda minus a to x plus alpha xj, what you get is that lambda minus a x is equal to z, and lambda minus a applied to alpha xj, it's alpha lambda xj minus axj, but axj it's equal to, because xj is the eigenfunction associated to the eigenvalue lambda j, it's equal to lambda j xj, and this is 0. So this is equal to z, and we get a new solution. So what we just proved is that if lambda is equal to lambda j, then there is no uniqueness of solution. So if there is one, there is infinitely many. So the fact that you have uniqueness of solutions implies that lambda is different from all lambda j. And we have seen that if lambda is different from lambda j for all j, then we can define an operator lambda minus a minus 1, which is a bounded linear operator, and that the solution z is given by the solution x, it's given by lambda minus a minus 1 z. So, and this is exactly the claim of the corollary, is that then lambda minus a, it's invertible, and the inverse, it's a bounded linear operator, and moreover, that the solution of this equation is given by lambda minus a minus 1 z. So I need some terminology to complete this lecture. So here, X can be a Banach space, though we are working on Hilbert spaces, but all these definitions can be introduced in a Banach space. So the first one, remember, is that we'll say that lambda, and we have an operator A from x to x, which is a bounded linear operator. So the first definition I already gave it, so let me just repeat. I will say that lambda is an eigenvalue of A if there exists x different from 0 such that Ax is equal to lambda x. Note that here lambda can be equal to 0, just that, well, I have x different from 0 such that Ax is equal to 0. So if the null space of A is different from 0, then lambda equal to 0, it's an eigenvalue. Then I will call rho of lambda of A. So let me assume also, I didn't say it, but let me assume that the field K is the complex plane. And so rho of A, this is the resolvent set. It's called the resolvent set. And it's defined as the set of all lambda in C, such that lambda minus A minus 1, it's a bounded operator. So you see, the resolvent is the set of all lambdas for which lambda minus A, it's a bijection, so I can define the inverse. And the inverse, it's a bounded linear operator. Linear, it's always, so I didn't say it, but let me mention it. So this is the resolvent set. And now we have the spectrum of A, and this is represented by sigma of A. And sigma of A, it's the complex plane minus the resolvent set of A. So here I defined the resolvent set of a bounded linear operator A and the spectrum of A by these two identities. So I forgot to say, but if lambda belongs to the resolvent row of A, then we call lambda minus A minus 1 the resolvent of A at lambda. So this is just a new terminology. Now, let's go back here. So we proved that if lambda is different from lambda j for all j, and lambda is different from 0, then we proved in the previous theorems that lambda minus A minus 1, it's a bounded linear operator. So this is telling us that the resolvent equation contains all these points. So what I want to say is, I need a definition. Let me call omega the set of lambda j's, the set of eigenvalues, which might include 0 because 0 might be an eigenvalue. Okay? But omega will be the set of eigenvalues. And what we just proved is that if you are different from omega and 0, then you belong to the resolvent equation. So if, just to make sure I add 0 to the set of eigenvalues, then any point which is not in this set, so in the complement of this set, belongs to the resolvent of A, because we proved that lambda minus A in this case is a bounded linear operator. So this always holds. Now I claim that omega is contained in the spectrum of A. Always. And this is clear because if I take an eigenvalue, if lambda is an eigenvalue of A, this means that there exists x different from 0 such that ax is equal to lambda x. And this tells us that, well, lambda minus A is not injective. Right? And since lambda minus A is not injective, lambda minus A minus 1 does not exist. The inverse of lambda minus A does not exist, and therefore it's not a bounded linear operator, so it doesn't belong to the spectrum, so it has to belong, it doesn't belong to the resolvent, so it has to belong to the spectrum. Okay. So these are two general facts, right? So that all eigenvalues are in the spectrum, and the complement of the eigenvalues with the origin are in the resolvent set. So this gives you a complete description in the case in which 0 is an eigenvalue. So if 0 is an eigenvalue, of A, then rho, the resolvent of A, it's the complement of omega, and the spectrum of A, it's omega. So we have just to consider the case in which 0 is not an eigenvalue. And this is the content of the next result. So the corollary is as follows. Assume that 0 is not an eigenvalue. Because if 0 is an eigenvalue, I have a complete description of the spectrum of A by the previous argument. So now I want to consider the other case in which 0 is not an eigenvalue. And what I claim is that if you are in dimension finite dimension, then 0 belongs to the irrelevant of A. While if you are in infinite dimension, then 0 belongs to the spectrum of A. So really, the finite and the infinite dimensional case are different just from the fact of 0 belonging either to the relevant or to the spectrum. Well, let's assume now that the dimension of X is finite. So 0 is not an eigenvalue, means that Ax equal to X implies that X equal to 0. So that means that this operator is injective. And now we know also that it has an inverse, that this has always a solution. And the solution, it's given by X equal to Z xj xj. So we have a basis made of eigenvalues and eigenvectors associated to the eigenvalue 0, but 0 is not an eigenvalue, so these are all eigenvectors. So this is the eigenfunctions associated to these eigenvalues lambda j form a basis of your space. So what I claim is that Ax equal to Z has always a solution which is given by that. So you can check now that if I take A here, I get Axj, this is lambda jxj, the lambda will cancel, and what I get is Z xj xj, which is Z. So indeed, Ax equal to Z has a solution. So this proves that this is surjective. So indeed, I can define the inverse. And the inverse, well, here is the solution. If you give me Z, I can find A up to that. And what I get is that x squared, which is therefore A minus 1 of Z squared, by this equation, this is the sum from G from 1 to N of Zxj square lambda j square. And all the lambda j's are different from 0. There are a finite number of them. So this is bounded by some constant which depends on these lambda j's. And this is equal to the constant times Z squared. So this proves that indeed A minus 1 is a bounded linear operator. So A minus 1 exists because it's injective and it's surjective. And this proves that A minus 1 is a bounded operator, which means that 0 belongs to the resolvent of A as we claimed. So let me just repeat the proof. I'm assuming here that the dimension is finite, and I'm assuming that 0 it's not an eigenvalue. So 0 not an eigenvalue means that if Ax is equal to 0, then x is equal to 0. And this is exactly saying that A is injective. Now, since 0 is not an eigenvalue, this means that in my previous decomposition of the space, or in my previous orthonormal basis of the space, all the wk's do not appear because the wk's are exactly the eigenfunctions associated to the eigenvalue 0, but 0 is not an eigenvalue by assumption. So I can form an orthonormal basis with eigenvalues eigenfunctions associated to eigenvalues which are non-zero. And I have just a finite number of them because I'm in dimension and infinite dimension. So x can be written in this way, where xj, it's an eigenfunction associated to the eigenvalue. Now, all what I'm saying, what I just said is that all y in x can be written as y xj xj from j from 1 to n, where xj it's an eigenfunction associated to eigenvalue lambda j, and lambda j is different from 0. So this comes from the fact that 0 is not an eigenvalue. Now, what I claim is that this equation has a solution. Take z in x. I define x in this way. This is well defined because all the lambda j's are different from 0, and this sum is finite, so this is well defined. Now I claim that x, it's a solution of this equation. Apply a to x. By linearity, you apply a to xj. This is lambda j xj. The lambda j cancel with that, and what you get is that ax, it's equal to z xj xj, and this is exactly z. So we proved that indeed x solves this equation, and this shows that a is surjective. So we have a linear operator which is a bijection. We can define a minus 1, which is a linear operator. It remains to show that a minus 1 is bounded. So let's look at a minus 1z, but a minus 1z it's x. X is given by this expression, so the square of the norm of x it's given by this sum. And since the lambda j's are finite, this sum is bounded by this one times a constant, a finite constant, which depends on lambda 1 and lambda n. And this is the norm of z, so this proves that indeed a minus 1 it's a bounded operator, and therefore that 0 belongs to the resolvent of a, because a minus 1, which is 0 minus a minus 1, it's a bounded linear operator. So this proves the corollary, the case in which the dimension is finite. So now let's assume that the dimension is infinite, and remember that 0 it's still not an eigenvalue. So here again, x, any y, can be written as a sum in J. And now we have infinitely many eigenfunctions because we are in infinite dimension of y xj xj. So this is an eigenfunction associated to lambda j, and we have that the limit of lambda j is equal to 0. Okay? And what I claim is that a minus 1 cannot be bounded. And cannot be bounded by the following reason, because a xj it's equal to lambda j xj. So assume that there exists a minus 1. I'm assuming that a minus 1 exists. Okay. If a minus 1 does not exist, this means that 0 belongs to the spectrum because it doesn't belong to the resolvent. So now let's assume that a minus 1 exists. Well, but what we have, since xj it's an eigenfunction associated to lambda j, is that this inequality holds, this identity holds. So if I call zj this element, what I get from that is that a xj it's equal to a minus 1 zj, and a minus 1 zj it's equal to xj, but xj it's zj divided by lambda j, and this tells me that the norm of a minus 1 zj it's equal to 1 of lambda j, the norm of zj, and this implies that the norm of a minus 1 it's larger than 1 of divided by lambda j, because I just plug zj inside here, and therefore I get that a minus 1, the norm of a minus 1 zj divided by the norm of j is larger than 1 over lambda j. Since the norm of a minus 1 is the soup of all that, what I get is that the norm should be larger than 1 over lambda j, but the lambda j's are going to 0, and here I have a norm, and this is going to plus infinity, so the norm has to be infinite, which means that 0 is not an element of the resolvent, and therefore it is an element of the spectrum. So let me repeat the argument. I'm considering that 0 is not an eigenvalue, and what I want to prove is that 0 belongs to the spectrum in infinite dimension. So here again, by my previous theorem, I can write y in terms of the eigenvalues. Since 0 is not an eigenvalue, I have not a sum over wk's, because the wk's are the eigenfunctions associated to eigenvalue 0, so they don't appear. And any element y can be written in this way, where xj is an eigenfunction. Fine. Now, well, there are two possibilities. Either a minus 1 exists, so a is surjective or not. If a is not surjective, this means that, well, 0 does not belong to the resolvent because, well, the inverse of a doesn't exist, so it belongs to the spectrum. Okay. So now let's consider the second case in which the inverse exists. So a is a bijection. What I claim is that, well, fine, there exists an inverse, but this inverse is not bounded. It cannot be bounded. Why it cannot be bounded? Because, well, let's take the eigenfunction xj. I have this identity, because xj is the eigenfunction associated to the eigenvalue lambda j. Let me call zj this element, and let me apply a minus 1 on both sides to get that xj is equal to a minus 1 zj. And let's recall that zj is lambda j xj, so that let me replace xj by zj divided by lambda j. From this identity, if I take the norms on both sides, I get this identity. Now if I divide that by zj, and I can do that because the norm of zj is different from 0, because lambda j is different from 0 and xj has norm equal to 1. So I can divide that by zj. And I recall that the norm of a minus 1 is the supremum of such an expressions. Then the norm of a minus 1 is larger than the norm of a minus 1 zj divided by the norm of zj. And therefore, the norm is bounded by below by 1 over lambda j. But 1 over lambda j, so the left-hand side does not depend on j. I can send lambda j to plus infinity, and this is converging to plus infinity because the lambda j's are going to 0. And therefore, from that I deduce that the norm of a minus 1 is infinite, and therefore a minus 1 is not bounded. If it exists, it's not a bounded operator, and therefore 0 does not belong to the resolvent, and therefore it has to belong to the spectrum. So we have we have proved this corollary, which gives us, in the case of symmetric compact operator, a complete description of the spectrum of the operator and therefore of its resolvent set.